Good day to supervisor, examiner, and reviewer. My name is Joshua Loi Kwang Yee, and today I will be presenting my final year project 1 with title Path Optimization for Coverage-Based Data Collection in Wireless Sensor Networks using Heuristic Techniques. This project is supervised by Associate Professor Dr. Sze under the Faculty of Computer Science and Information Technology, University Malaysia Sarawak. First, let me introduce about the background of wireless sensor networks. Wireless sensor networks, or WSNs, it consists of numerous small sensor nodes that collect and transmit environmental data wirelessly. Their significance lies not only in their technical novelty, but also in their ability to enable real-time, large-scale monitoring in domains critical to human life and societal progress. From environmental monitoring and smart agriculture to industrial automation, disaster management, and security surveillance. Wireless sensor networks provide backbone for intelligent decision-making in contexts where traditional wired systems are impractical or impossible. To save energy, mobile sync often being used. It is a moving collector used to gather data from these sensors. The mobile sync will move through the sensor nodes in a particular area and collect data from these sensors. However, the biggest challenge is ensuring full coverage while keeping the sync's movement efficient. Planning an effective path for a mobile sync is challenging due to constraints such as energy limitation, travel time, distance cost. The path must minimize energy consumption and delays while visiting all nodes reliably. Poorly planned paths lead to incomplete coverage, high energy usage, long travel distance, and ultimately reduce the network lifetime. The problem faced is to ensure all sensor nodes are effectively covered during data collection, particularly when the mobile sync must traverse multiple sensing regions. Inefficient path planning can lead to incomplete coverage, excessive travel distance, and high energy usage, which will reduce the overall efficiency of the network. Furthermore, one key issue when using mobile syncs is maintaining uninterrupted data collection and conserving energy. As the sync's position constantly changes, data reports from sensor nodes may be lost when the previously valid path becomes invalid due to the sync's movement. Therefore, an intelligent path planning strategy is required to optimize the mobile sync's traversal path by minimizing total travel distance while maintaining full coverage of the sensor field. This project focused on implementing heuristic algorithms, evaluating performance based on path length and coverage ratio, and also visualization of the mobile sync's path using MATLAB while excluding real hardware implementation and only consider static sensor nodes, and factors such as transfer speed, round trip time, sensing models, and node types are excluded. In order to solve the problem, my project has three main goals. First, to design a coverage-based path planning model. Second, to apply heuristic algorithms like nearest neighbor and insertion method. And third, to evaluate their performance based on distance. This project adopts the Agile development methodology. The overall process consists of five main phases, which are phase 1, requirement analysis, where the main objective is identified, the system requirements are defined, and the heuristic algorithms to be applied is determined. And phase 2 is system design, where the simulation framework using MATLAB is being designed, and the algorithm flow diagrams and pseudocode for the method used is being created. And third, phase 3 is implementation, where the developing and refining of MATLAB script for algorithm used in iterative cycles, and also conduct internal evaluations to identify improvements or code optimizations. And phase 4 is testing and evaluation, where the visualizations and simulation of the result using MATLAB props, and also compare and analyze the result. And last but not least, the phase 5 is analysis and documentation, where a final review will be conducted on the result and summarize the finding, and all phases of the project, including methodology, implementation details, result, and conclusion, are being documented. This project contributes to energy efficient operations through optimized path planning. It also improves the network lifetime by minimizing the redundant sync movement, and also it has some educational value because it provides a simulation tool that demonstrates heuristic algorithm behavior in real-world scenario. During the literature review phases, I had read through some article about finding rendezvous points using clustering method and geometric intersection theory. I had also do some research in optimal path planning using simple heuristic methods, which are nearest neighbor heuristic and simple insertion heuristic. The project is needed because this research focuses on single hop direct communication, which a sensor nodes only transfer data to mobile sync. But other research focus on multi-hop data forwarding techniques, which sensor nodes not only transfer data to mobile sync, but also to other sensor nodes. This study focused on identifying the most efficient points, which are the rendezvous points within overlapping sensing regions, and also determine the shortest route for the mobile sync to traverse all rendezvous points and standalone sensing ranges. From the diagram behind, we can see the overlapping region in red color and the route in red dotted line. MATLAB is used for the simulation purpose. The setup involves 10 stationary nodes with a 1 meter sensing radius. I followed an agile methodology which allowed me to iteratively refine the code and the algorithm logic. In this study, the following constraints and parameters are established. First, all nodes are stationary and possesses uniform sensing and communication capabilities. Secondly, wireless links are assumed to be ideal, excluding factors such as interference or packet loss. Third, the mobile sync must complete a cross-tour, starting and ending at a fixed base station located at coordinate 00. And overlapping regions of all the nodes are limited to a maximum of 2 nodes with a maximum overlap depth of 0.5 meter. Next, let us look at the overall flowchart. The diagram shows the overall flowchart for the proposed two-stage approach for this study. First, initialize the simulation environment. Second, identify the overlaps and replace the overlapping nodes with a candidate point. Third, using heuristic method to find the nearest target and select the best candidate point for the mobile sync. Lastly, return to the final tour and calculate the total distance. In stage 1, which is identify the overlaps, it will first have a loop that searches through overlapping on each sensor nodes. An overlap occurs if the distance between two nodes are less than 2 meter, which is 2 times radius size. Then it will calculate for the overlap region between both nodes. The region is being coded as region B. 5 candidate points will be generated for that region B, and the 5 candidate points are centroid and 4 cardinal extreme. These 5 points is shown on the diagram on the bottom left, where the black dot is the centroid and the 4 red crossed are the cardinal extreme points. The two nodes location will be replaced by 5 candidate points when all nodes is being checked. Stage 1 is done and stage 2 start. In stage 2, which is heuristic traversal, the algorithm will detect whether unvisited nodes is empty or not. If it is not empty, It will find the next nearest target to the current node that the mobile sync stays. If the next stop is an overlapping region, the algorithm will find the shortest point from current node to these overlapping region candidates. The best candidates will become the target point, then the total distance will be updated, and the algorithm will rerun until the unvisited target is empty. If the unvisited target is empty, the mobile sync will return to the base station, which is coordinate 00, and return the final tour together with the total distance. Finally, the expected outcome of this project is a simulation tool that demonstrates how this heuristic can reduce redundant movement. I expect to show that by visiting overlap regions, we can significantly extend network life and provide a more reliable way to collect the data. As a conclusion, this research proposes a coverage-based path optimization approach by combining geometric modeling and also heuristic techniques. That's all about my FYP1 presentation. Thank you.